So let's go ahead and get into it. We're moving away from binomial and into geometric, and there's a lot of similarities and a few differences. So let's just go for it. There are going to be 4 conditions for a geometric distribution, just like there are 4 conditions for a binomial distribution. In fact, they're almost identical. Let's just start. So there are 2 possible outcomes, success or failure. Sounds familiar. All your trials are independent, so knowing that one thing happened or was a success doesn't tell you what comes next. Probability of success remains constant for each observation, so we've really hit all of the 3 that the 2 share in common. Where they differ is with the last one. Here, the variable of interest, or n, represents the number of trials until the first success occurs. That's why I wrote it in that green color, because that's where it's different. All right? So, what's the probability that my first measles patient is the 5th kid I test, or the 10th kid I test, given a certain probability, given that, measles cases are independent of each other, all this kind of stuff. So it's different. It's a little different, but it's very calculator intensive, so we'll kind of mix that in with it. All right, always define your random variable. So x is the number of trials until the first whatever is observed. The first A on a test is observed. The first, home run is observed. The whatever. All right. So the big difference between binomial and geometric is that there is not a fixed number of trials in a geometric distribution. I mean, think about it. If I am a 70% free throw shooter, then you might be interested in when I make my first free throw. Well, it could be the first one. It could be the 4th one. It could be the 10th one. It could be the 100th one. There's no end to it. It's an open-ended kind of a distribution, unlike binomial where it stops. 5 girls out of 7 kids. 7 kids is it. There's no 8, 9, or 10, right? But if I were to ask you, what's the probability that the first girl is the 5th kid born, or at least the 5th kid born, or at most the 5th kid born, that's all geometric. See the difference? That's one big difference. Another difference is that binomial random variables start with 0, because if I want to know the probability of, let's say, at most 3 girls out of 5 births, well, that would be 0 or 1 or 2 or 3. Right? You have to have the possibility that there would be no girls, right? But a geometric random variable has to start with 1, because if the first girl is observed by the whatever birth, well, there's got to be a birth, right? So it's either the first birth or the second or the third or the fourth. You know what I'm saying? So it can't start with 0, because you can't have a kid of a boy or a girl gender without a birth. So it always has to start with 1. I cannot make a free throw if I don't make a shot. So that's a big difference. Binomial distributions are finite, while geometric distributions are infinite. Strangely enough, they're still both random variables, so even though a geometric distribution is infinite, all of the probabilities still add up to 1. Right? So there's your, what am I thinking of? Your limits in action. Okay, here are your formulas, all right? So this is how you calculate a geometric PDF, right here, the thing I'm circling. And all it is your number of failures times the probability of success. So 1 minus that probability of success would constitute probability of a failure. And it's going to be x minus 1, because if it's by the first, let's just say your first girl is by the 5th kid you have, then you've got to have 4 boys ahead of the girl, right? So that would be x minus 1, x being 5, oh, I think I've totally messed that up. I forgot what my numbers were. Let's start over. Okay, so if your first girl is by the 5th birth, then there have to be 4 boys ahead of that. So 1 minus p would be the probability of a boy, and x would be 5, so x minus 1 would be a boy and a boy and a boy and a boy, and then that p would be and a girl. All right, does that make sense? Whew. All right, the mean of your distribution will be 1 over the probability, and the standard deviation is a little bit complicated. All right, 1 minus p over p squared is variance. Take the square root of that, and you get standard deviation. This is just a variant of it, an algebraic variant. So this is a geometric PDF. This is the mean, how you calculate it for a geometric random variable. And this is the formula right here for standard deviation. Okay, you're going to need to know those just the same way you had to know the ones for binomial. All right, so count the number of boys in a family of 4 children. Well, there may be no boys, but count the number of children until a son is born. Well, you've got to have, a birth so that you can get a son. So there's no 0 here. That's just to emphasize that. And it's open-ended. This stops. All right, so you have a geometric PDF in your calculator, which is for exact values. That your first boy is the 3rd child, is exactly the 3rd child, born. And then you have a geometric CDF for things like at least, at most, less than, greater than. This is going to find your cumulative probability, and in your calculator it's going to be p lower bound, upper bound. And if it's going toward the infinite for upper bound, you can put in a big number like 10,000 or something like that, and you'll get the exact answer. All right. So what is the probability that the first son is the 4th child born? All right, that is a PDF. So it's a geometric PDF, and all it is the probability and then whatever x is, right? And out it comes. What's the probability that the first son born is at most the 4th child? Well, that's going to be a CDF, 0.5, and then from 1 to 4. All right? And then what is the probability that the first son born is at least the 3rd child? Well, that would be the 4th or the 5th or the 6th on indefinitely. So that would be, let's just use this. This is for the old calculator. But for us, it'll be a geometric CDF 0.5 from 3 to infinity. Well, don't put infinity in there. Put some big number, like 10,000 or even 1,000, something like that. So let me call those up, and we'll shrink this down. So let me show you where these things are. So, so you just get to your calculator and go to your home screen, and it's just going to be where all of your other normal CDF, binomial CDF, all those are located. So it'll be menu. Okay. Oh, is this frozen by chance? Try it again. Well, okay. I guess I need to be in like a scratch pad or something, so let's try that. Okay. So menu and probability and distributions, same old. And if you scroll, you will find geometric PDF and geometric CDF, right? That first question was, your first son is by the 4th birth. So having a kid, any kid, boy or girl, would be a probability of 0.5, and then the x value would be 4, and then just tab down to OK, and you're good to go. All right. If it's by at most the 4th birth, then that's either the 1st, the 2nd, the 3rd, or the 4th. So that's a CDF. Okay, so again, probability, distributions. Now this time we'll find geometric CDF. This thing is just not wanting to play nice with me. But again, you know this is live TV. So let's see if we can't, come on, scroll. I know it's here somewhere, it's just playing games with me. All right, I probably ought to pause at this point, but now it's a matter of pride. All right, let's see if it'll go up. Let me use the down arrow. Come on, go. Don't keep going backwards. Finally, there it is. All right, so we'll choose that. Probability of success will be 0.5 again. So 0.5. And this will automatically start with 1. Now you can change that 1. You can say, like between the second and the 10th kid inclusive, you can put a 2 and a 10 in there. But for here, we're starting from 1 and going up to 4, so we can just leave that. And then tab down to OK. And there it is. All right, now I'm just going to go up here and do this trick to keep away from that menu. All right, and that was by at least the 4th birth. Okay, so we'll just go in here and we'll change this to 4. And then this is really infinity, right? But we'll just put in some big number like 10,000, just something big. Okay, and it'll give you, that's exact. Because there's so little probability after a certain value for x that it's just going to default to this. All right, so I think we got all 3 of them. We did. Okay, so let me get this back up. And from current slide. All right, so we did those 3. All right, so a real estate agent shows a house to prospective buyers. The probability the house will be sold to the person is 35%. What is the probability the agent sells the house to the 3rd person she shows it to? All right, so that is a PDF because it's not, sell it to the 3rd person exactly. So it's just 0.35 comma 3. So there's your answer. How many prospective buyers does she expect to show the house to before somebody buys the house? All right, that's just 1 over 0.35, which is a little under 3 buyers. Don't round it. And then the standard deviation, just plop it in the into the formula. I tend to not forget this formula. It's 1 minus p over p squared and take the square root. All right. So there it is. That's geometric probability. All right, so go ahead and do the geometric probability distribution worksheet. Since you already know binomials so well, may very well be a mixture. There may be an occasional binomial question. You'll be able to tell because there is a fixed number of trials, right? As opposed to when do we get what we want by whichever trial, right? So I'm just going to call it a night, and I will see you on Friday.